Hello and welcome to day 2 of the second week of the CAS Virtual Showcase. You've joined the first webinar of the afternoon entitled Tools and Strategies for Teaching Programming at Key Stage 3. This webinar is part of the CAS Virtual Showcase, which is a 2-week window of webinars designed to support the CAS community. I'm Wendy McLeod and I am the CAS Community Outreach Manager for communities across London and the East of England. Joining me this afternoon is the presenter of our session, Rebecca de Cruz. Rebecca works as a lecturer and has a background in commercial software development. Rebecca found herself well placed to support the emerging computing curriculum in schools. Through developing and running CPD, co-leading CAS East and leading programming lessons, she eventually took the plunge and switched to working full-time in a secondary school. She had the great opportunity of creating a computing department at St Albans School from the ground up and has single-handedly developed the department to its first year of A-levels. She also supports Ocado Technology as their educational consultant. During the session, please use the question window on the right-hand side of your screen to ask questions. All attendees are in listen-only mode. The top of the window has an orange rectangle which can be expanded or collapsed, and the slide presentation can be downloaded from the handouts section. If using social media, the hashtag for the event is hashtag CASVirtual20. I'm now going to hand over to Rebecca for the session.
Wow, Wendy, that was slick. I saw you set the bar really high. And thank you for that introduction. Blimey, great. I don't need to say anything about me anymore. That's wonderful. Thank you, Wendy. So fabulous. Welcome, all of you. I hope you're going to find this a useful talk on teaching programming at Key Stage 3, different strategies and tools that I've employed and continue to employ. So let's get started. So my first experience of computer programming when I was 12. I was really lucky to get hold of a Sinclair ZX Spectrum. Now, bearing in mind, I was in Kenya, this was pretty unusual. I got this computer home and that was me, I was lost. I took over the family television because that was how it worked in those days, plugged in, that was it. And I taught myself to program and I've just been lost ever since. I've loved it ever since. And yes, I spent ages putting that little Lego model together. What can I say? I had a first career in software development, working in banks in the city and all sorts of things. And as you can probably tell from the picture I've chosen, I don't miss that very much. I went on to lecture, so I moved into education by lecturing at the University of Hertfordshire. And I also, as Wendy said, co-led CAS East from there. I moved on to St Albans School. I'm going into my 5th year now, blimey. And as Wendy said, I set up the department, which I feel really lucky to do. I've had lots of autonomy and I thoroughly enjoy that. And I continue to work there full time. So I'm not a lecturer anymore. I'm a teacher. I work full time as a teacher. And as Wendy also said, I'm an educational consultant for Code for Life. So Code for Life produce free educational tools. And I see my role very much as sitting between the weird and wonderful world of education and the weird and wonderful world of software development. So I feel that I can sort of translate there, get a lot out of that. And I'm a facilitator for the NCCE. I run some courses with them as well. So why am I telling you all this? Because in some ways I feel that my background in programming and software development really helps me, but I found it took me a long time to work out why novice programmers found programming hard, because I've been doing it for such a long time. It was so native to me. I just couldn't work out what they thought, why it was difficult. And I feel that particularly if you're coming from the point of not having done very much programming, or not having a degree in computer science, or not having a software development background, in some ways that helps you, because your journey is really fresh. You've been through the challenges of learning to program, all the resilience, all those sorts of things are really fresh in your mind, and you can bring those to your teaching. So that can be a really, really big benefit. So I think we would all agree that teaching and learning programming is hard, one of the hardest parts of the computer science curriculum. Why? I think one of the things is people don't realize that programming is really a practical skill. It's not something you can learn from a book. It's not something you can just read and think about. It's a practical skill. You really, really have to practice. And students find that very difficult to understand. But on top of that, you're also teaching a way of thinking. So you're teaching students how to approach something in a really slow and methodical way, and that's hard. Trying to teach that experience is also hard, and it requires these skills we talk about so much of persistence, resilience, and curiosity. And I think that the problem is when we start teaching particularly things like text-based programming at Key Stage 3, kids are becoming teenagers. They're questioning their whole existence, all these existential questions, and actually at this point asking them to be persistent and resilient is quite a tough ask. They found that quite hard. I show this picture to my students in year 9 when I start to teach programming to them, and I say, well, first thing is, can anyone do this? And no one ever can. And then I say, well, okay, well, if you were going to do this, would you just go and do it? Would you just get your bike and go and do that? And obviously, no, they wouldn't. They would not expect to do something as hard as that without a huge amount of practice and baby steps and falling off and all that sort of thing. So I try being really the operative word to get them to understand that this is similar to programming. You do have to take baby steps, you do have to fail, you do have to be really resilient and persistent. Curiosity is an interesting one. I felt that one of the things, because I was self-taught, because I absolutely taught myself to program from a book, because there wasn't any other way. My parents certainly didn't have a clue. Curiosity was one of the things. I really want to know what would happen. And I think that pupils can really be lacking that sense of curiosity. So we have to try to embed that in the way we teach. Oops, sorry, I didn't do that. There we go. So the thing again about programming is it looks easy until you actually do it. And I think this is also true when as a teacher you're presenting a concept, you can feel the pupils are like, yeah, this is easy. But actually they need to do it, and that's the hard bit, and they can find that a little bit misleading as well. And rote learning doesn't help them, and this can really let some of them down, because you get, and this is, so I teach in an academically selective school, but I have a really broad range of pupils and their ability in terms of programming. And actually some of the really bright ones can find programming hard because they're very used to just learning stuff. They're very used to going, well, I know this, and it doesn't help them with programming. They really have to think about it. So the analogy I use a great deal when I'm talking about teaching programming is sculpting. And I said, if I was a master sculptor, which I'm certainly not, and I was going to teach you to sculpt, we would get the tools and we would pick up a tool and we'd talk about it. We'd say, well, this is what it is and this is how it works. And I would do a tiny little demonstration and I would show you something. And then I would let you have a go. And it would take a lot of time before you could make any, even to use the tool in any kind of sensible way, let alone make any sort of recognizable shape, let alone create David. And it's not just learning each tool, because you pick up a tool, you learn, you practice, and then you pick up the next tool and you learn and practice. And then you might feel that you're quite competent in using those tools. But actually the bigger problem of being faced with a block of marble and knowing which tools to pick up, how to combine them, that's a further difficulty. And so that again completely relates to programming. So we teach a concept in tiny steps. The pupils practice, they go, oh yeah, I get that. Then we teach another concept and they practice. But actually when you then face them with a question that requires them to pull those concepts together and to choose which one to use when, that's a further challenge. So don't ever assume that they can just do that, because it's definitely an additional challenge on top. So spiral curriculum. I've taught maths in the past and I love maths, and I think that this is really related. I think, we're all used to maths being taught as a spiral curriculum, but I feel very strongly that programming specifically, and it also applies to other parts of the computer science curriculum, but programming in particular really needs a spiral curriculum. So we're all used to seeing these terms, so decomposition and pattern recognition and abstraction, the sort of cornerstones of computational thinking. So we have to introduce these slowly, and as we go around our spiral, we add more complexity, but don't ever think you can teach it in one hit, because you can't. And equally, when we start thinking about sequence and selection and iteration, each of these skills has to be reinforced. So we start with small things, we add on, and we come back. And I think it's important to spread that through your curriculum. So this is part of my curriculum at school. I've just sort of pulled out the programming strands basically. And as you will see, the underpinning thing here is computational thinking. And I think this has to be part, whether sort of implicit or explicit of all the things that are building up your programming skills. So I will talk about how I do these in different ways. Block-based programming as well is so important. Don't be persuaded that it's just for primary. It certainly isn't. I use block programming, as you can see, right up into year 9 for reasons that we'll talk about. So you'll see that those things spread through each year, and they allow you to hopefully, when you get to the point, well, when we get to the point in year 9 when we start teaching Python, that there would have been a build through from the computational thinking exercises, the block-based programming, things like BEBRAS, using Rapid Router, using microbits, using flowcharts in different guises, that they've had the practice of all the thinking skills, so that takes away some of the challenges that they're faced with in terms of block-based programming. Sorry, in terms of text-based programming like Python. You'll notice I also use the LMC in year 9, the Little Man Computer. So while I was doing research for this talk, I found myself pulling together information from all sorts of places, and I felt I needed to put it somewhere before I could kind of coalesce it and make a presentation out of it. So I ended up creating this website. It's just on Google Sites. And if you are interested in finding out more about these things, I've delve down a lot more deeply into each of these things on that site. So feel free to have a look at that and see if you find it helpful. And all the links are there. They're in this presentation as well, but they're in there too. Right, so computational thinking. So we've all heard a lot about computational thinking, and it really does need to be the cornerstone in terms of teaching programming, because it's, as you say, it's not a rote skill. We have to teach them to sort of break things down. So I would argue this, as I said already, this needs to be part of all of those things. It's not a particular unit. It's threaded into lots of different areas of the curriculum. So talking about things like breaking down a complex problem into smaller tasks, finding patterns, abstracting, and thinking about algorithm design. So one of the things I use throughout the school is Chris Roffey's wonderful BEBRAS challenges. If you haven't come across those, I would highly recommend you look them up, because they really get the kids thinking. That there's some programming in them, but actually an awful lot of them, particularly with the younger years, are really about puzzles and trying to work things out. In the first form, on one of my units, I use this paper plane exercise. So I get, because one of the things that pupils find difficult to understand is how they can write instructions in a way that is unambiguous. So we get them to do an exercise where we say, right, okay, you're going to make a paper aeroplane in a fairly simple way and write down the steps as clearly as you can. And you can either write them or you can draw, all these sorts of things. And then they swap with a different pair and try to make the aeroplane. And then they critique the instructions, because so often they think they've written it really clearly, but it's really ambiguous. So this is just one of the steps that I use to try to get them to think about instruction making. We also do things like card tricks. So I will show them simple card tricks and get them to try to puzzle out what's going on and get them to write down instructions for that, and talk about things like, well, if you were to go home and you were going to leave some instructions for your parents so that they could learn this card trick, how could you write them down so that you didn't need to be there to explain? Other resources I use are things like Dr. John Snow's map of the cholera outbreak. So this is quite a nice computational thinking exercise that we use. And of course, we couldn't possibly forget about Phil Bagg's jam sandwich robot. If you haven't come across this, it's a wonderful thing. There are lots of different videos out there, including this one, if that's Phil himself. And it's, for those of you who've not come across it at all, essentially it's the idea of making either a jam sandwich or a peanut butter and jelly sandwich, depending on which side of the pond you're from. And again, pupils understand how to make a sandwich. They think it's easy, but the approach you take is that you slavishly follow the instructions you're given by the pupils, to great hilarity, as I'm sure you can imagine, but it does get them to think about being unambiguous in their instructions. So block-based programming, as I said, don't underestimate block-based programming. It's accessible to everybody. So in terms of different abilities, children with dyslexia, children who struggle with all sorts of things, will find the block-based programming approach straightforward, and more straightforward. And if you're careful in your choice of block-based programming, then you're not actually taking the difficulty away. So there are certain block-based programming tools that I'm not keen on that have things like score blocks where there's too much embedded on them. I think that they need to be algorithmically, the pupils still need to think algorithmically, not have too much thrown at them. Because of course one of the challenges, particularly if you're writing games or something, as is often the case with some of these block-based programs, is the kids are so used to opening their computer or opening their phone, and they've got this whiz-bang game that does all sorts of things, and they go, I want to write that. Well, of course they can't, because they're incredibly complicated, and so it's difficult to get them to be satisfied with the things that they can do. But block-based programming is certainly a really good approach. It allows you to teach the algorithmic thinking and the breaking down of problems without worrying about things like syntax. So this, of course, helps with this whole thing we talk about a lot, with good reason, of cognitive overload, because if your pupils are struggling with how to structure something in terms of the sort of language the computer needs to use in terms of the granularity of the steps required, they're also sort of trying to grapple with the problem they're trying to solve. If you then throw on top of that the need for complex syntax, so you've got brackets and you've got tabs and you've got case, it's too much, and you'll find that pupils will just find that too much. So using block-based programming helps to sort of deal with that, and generally the motivation is high. Lots of these things are more sort of colourful and more game-like, and so pupils are quite keen to actually use these environments. So Scratch I have used in the past. I don't use it anymore. Scratch is wonderful, don't get me wrong, but because it's so open-ended, you as a teacher have to be very, very careful to structure it. And I stopped using Scratch because I found I was teaching Scratch too much. I was teaching about the foibles of Scratch rather than programming. So that, don't use it anymore. But other things I use are things like Lightbot. Now this is the old Flash version of Lightbot, which I miss because it was definitely better than the ones that are available now. But Lightbot is great because if you haven't come across this, you've got this little robot moving around a factory, and let me get my pointer in the right place. You've got very few commands you can give it. You can give it forwards, turn right, turn left, jump, turn on the light, which is what it's trying to do, and you've got a couple of function spaces as well. So he's trying to turn on these little blue things to make lights in the factory. So that really gets them thinking. That was a great. The Lightbot is still available in different guises, and it's on an app and things, but it is still available. Rapid Router I use a lot. I've been using Rapid Router for a long time, and that's how I got involved with Code for Life. So I'm not here to sell it to you. I've been using it for years. It's completely free for life, including all the teaching resources. What I like about this, the reason I prefer it to Scratch in this scenario, is it's structured. So you've got the lessons building up the concepts as you go. And this scoring that you can see here is you get 2 scores. You get 1 score for the route. So did you get where you were trying to go? And you get another score for your algorithm. So did you choose the most efficient route, which is nice. And you'll find that pupils will compete with themselves and go, oh, I only got 6 out of 10 on my algorithm score. Why was that? And some of them don't, some of them just move on. But that's children for you with different approaches. And some of them will really want to know how they can improve it, which is great to see. But they really enjoy using it and they get a lot out of it. It's certainly still teaching all of those skills. The microbit, I'm sure lots of you have come across microbits, and there are so many good resources. There's been a huge amount of work on the microbit project over the last year or so. There are loads of resources on their website. Have a look at that. I use that we call them different things. I have to keep translating to year 7. So I use them in year 7 as their sort of second hit at programming. So the first programming they do is with Rapid Router, and then we do some microbit programming. And I also use it as a gentle way to introduce physical computing. So we talk about things like sensors and buttons and accelerometers and the compass and those kinds of things. And I try to link back the concepts we've already discussed. So when we were doing Rapid Router, I don't just say, right, there's Rapid Router, get on with it. We talk about selection, we talk about variables, we talk about loops, talk about conditions. And so they know these words. I think it's important to use technical terminology right from the beginning and keep doing it. And so I try to sort of link that back. So they're trying to make those connections. So flowcharts, wow, that brings back memories for me. When I did an O-level, yeah, I'm that old, in computer science way back when, and we had to draw flowcharts by hand, and we had a template very similar to that. It's not quite the same. I couldn't find a picture of the exact one, but you had to draw them by hand. So you had to draw the shapes in. And of course, it was an absolute disaster if you made a mistake because you had to rub it out and start again. It was awful. But the thing about flowcharts is, again, trying to persuade pupils to plan their approach to things without having to worry about syntax. These days, you've got all really nice runnable flowcharts, and I use those in preference. Things that with physical mimics like Flowwool, for example. Flowwool you do need to pay for, but to be honest, I think if you can afford it, it's worth it. You have, this thing is called a mimic. So you've got your flowcharts, which are very traditional flowcharts. They look just like the flowcharts you'd find at GCSE. They're absolutely correct. But what you have here is a physical mimic. So this, in this greenhouse, for example, you can turn on the lights and the lights will change in the picture and the window will physically seem to open, it will move, and the sprinkler will show water. So they actually physically see something happening on the screen. And I think that's really important because it, in terms of abstraction, in terms of them having the ability to just be within the flowchart and sort of trace it in their heads or on paper, that's a real challenge. But when they can see something actually happening, they understand the effect of what they're doing more, and they're more willing to try to fix it. So of course, this is a program really. It's just a program expressed as a flowchart. Or start to encourage decomposition right from the beginning. I think it's important to try to get them to think about breaking something down. And particularly when they start to find things hard, I would always go back to, right, what is the simplest part of this? Let's do that. Let's get that bit working. Then let's add on and get that bit working, and then we'll add on. Because if they start to try to do the whole thing at once, then they're likely to fall over and then create a spaghetti mess they can't get out of, and then they lose heart and all of those things. So little baby steps, I think it's really important, but probably don't use that term. So I also introduced testing, particularly when I move on to Raptor. So this is free. You can to install it though. It doesn't run in a browser, which is a pity. It doesn't run on Macs either, but it's worth it if you have Windows PCs. I find it really excellent. So again, it's very traditional flow charting. The diamonds are a bit peculiar looking, but you've got these additional arrows for input and output, which is quite nice, but not necessary. So what you end up with here is a much more sort of text-based approach, but it leads on from the sort of Flowwool. And what I've started to do in this unit, and I use this in year 9, I use Flowwool in year 8 and Raptor in year 9, is I get them to start thinking about testing. So this example, I don't know how well you can see it, is just a very dull, sorry, but they kind of are programming questions, aren't they sometimes? How old are you? Are you old enough to drive, sort of thing? And so I get them to say, well, how do I test this? How do you know that your flowchart is correct? What values do you need to test it with? So, okay, so if you enter 16, what should happen? If you enter 17, what should happen? And get them to think about testing. It's not their favorite thing. And I link back when I teach programming. So when I go to teach Python, I will bring in flowcharts. I will bring this exact flowchart into the teaching slides, and then we will relate that to a program. So again, I'm trying to link their knowledge. So finally, I spent an entire term teaching programming, text-based programming with Python in year 9. And even then, I find it astonishing that I don't even get as far as loops. It takes an entire term and I see them twice a week. There's a huge amount of practice that's needed with programming, and I think it's a mistake to rush it. I think you really need to take time. The vast majority of schools in the UK use Python with good reason. It's very sort of linked to things like pseudocode. It's very step by step. So I'd highly recommend using Python. It's free, of course, it's open source, and it's got all sorts of different paradigms. So it's got the imperative paradigm, which means that you just going step by step. You don't need to include subroutines. Then, of course, procedural, where you're actually using subroutines. You can also use it for object-oriented coding for A-level. That's only in A-level. So it's really flexible in that respect. Just from a personal thing, you're way ahead to the A-level. I don't actually use Python for A-level. I use Java, but you can use Python for A-level, and a lot of schools do. It is relatively simple to learn. It's relatively straightforward. You haven't got the overload of a lot of other things going on, but also it's not a toy language. It's not just used in education, because you start to find that parents and pupils are a bit more sensitive to that. What's the point of learning this language? Well, it is used commercially and increasingly. But, you know, we are teaching skills. We're not teaching Python. I try to be careful with my words. We are teaching programming and using Python as a tool, but I would argue it's a good tool. So what I think is important is to continue to use the strategies that we've been using right through from year 7. You don't just get Python and go, right, let's learn Python. Those skills need to be built up, and you need to support and embed and extend and keep doing that. And I referred to this earlier. I find that, and it's something you need to be quite strong with as a teacher, you can be explaining something and the pupils are starting to look a little bit bored, because they get it. They understand what you're saying. Intellectually, what you're saying makes sense. But actually, when they try to do even that small thing, they can find it quite hard. So do expect that, and don't assume just because they seem to understand what you're saying that they're going to be able to do it in terms of programming. Oops, sorry, I just heard noise. I don't know what it was. So I think it's really important that you talk about algorithmic problems and talk about them step by step, and think about the formal language. It's quite a challenge for them. So there are so many different pedagogical approaches around, and I have to say that actively in my lessons I use every single one of those apart from pair programming, surprisingly, and I don't think that's too heavy. I think you do need to mix these things up. I'm going to talk about just a few of them. I'm going to talk about those 3 in a little bit more detail. So this is where I start with programming. I will talk about a little bit of the sort of theory aspect of something, you know, even if it's just an input statement or selection or something like that. And I will demonstrate it. I will demonstrate it in concept, and I often write pseudocode on the board, even though I'm not teaching them pseudocode, because it's a good sort of, I can't think of the word now, it's gone. They can understand it, and we're not worrying about syntax. So I'll often use that to demonstrate a concept and discuss it. And then I will ask them to do pretty much what I just did, because it helps them to just reinforce what they just understood. It's really important not to rush, because you'll be surprised that it does take a certain amount of time for them to process it. Before I even get to add any more complexity, I often give them a resource that they can use. I've written some online resources where they can sort of practice and extend that slowly. But it's really important that when you start to make things more complex, I feel that you add that really slowly, because it becomes overload. So I said earlier when I was talking about the sculpting tool that it's much more difficult to choose and combine. So it's much more difficult to go, right, I've got sequence, selection, iteration, I've got a problem, how do I use those things to answer this? Those questions there are quite hard. So find the average of 5 input numbers, assuming you're using a loop, not straightforward, the highest number in a list of marks, and validate an input code. Those are all things that actually, unless you're talking about a fairly experienced class, even in Key Stage 4, take quite a lot of building up to do. I think it's really, really important that you model. I think you need to really show pupils. You can talk as much as you like, but it's not until you show that they start to really sort of feel that they need to know what they're doing. So you need to show them how to decompose. You need to take a problem and physically break it down on the board for them so they can start to understand how to do that. Incremental development is really important. I think it's a really big mistake for a teacher, even if you're feeling less confident, to come in with a solution and go, there's the Python program for that, because all they've learned from that is that you're cleverer than they are, and they won't learn how to get there. So if that's what you've done, work backwards and go, right, what was the first thing I did? And the first thing can simply be an input statement. And then what do I add? And then what do I add, with testing in between, because it builds up their confidence they're getting somewhere. And that's really important if you don't want them to lose heart. Live coding, if you can brave it, is brilliant. And even when you make mistakes and when you get stuck, that's fine. I typed things out before and gone, what have I done? And it's fine to do that. And you'll find that pupils will help you, and that's wonderful. So I think live coding is a really, really strong thing to do. The example I want to show you is I'm going to show you reasonably quickly because I talked too much and it's past and we've only got 15 minutes left. This is the Key Stage 4 example, but I want to show you what I mean. So given this question, so search a given list for an input color and output whether it was found or not. Now, Key Stage 4, this I would not teach to an early programming class. I would teach this in a GCSE class, but I would encourage them to take this approach. So let's start up. We've got a list. There we are. We've got a list of colors. Fantastic. So the first step, I would say, is to output everything in that list. So to create a loop that outputs everything in that list and then run that and make sure that works. Because if that doesn't work, if you can't do that, you can't do the next thing. So that's the first step. And then I would say the thing to add to that is just to ask the user what color they want. So you just add an input statement, what color do you want to find? We're not using it, nothing's changed otherwise. And then we run it and we test it, fine. And then we say, right, how do we know if we've found a match? What is the point where we know about the color we're looking at? And we get them to identify it's got to be inside the loop. And then this leads us slowly into adding the selection statement and saying we have found it. Now, it's important to think about this beforehand. It's much easier to know you have found something than not found something. So start with that. And again, run it, test it, make sure it works. So we've got found blue there in the middle of our loop as well, and that's important. And finally, and this is the final thing of it's found or not. And this is where we need to think about we hadn't found it. If false is still not found at the end of the program, then you know it wasn't found. But you can see how we can build that up in a way that makes it much, much more accessible. Okay. So all of these things I would say are really key. So focusing on problem decomposition, planning, live coding, incremental development, we talked about hand tracing. So trace tables are part of the GCSE, but we're not focusing on the GCSE. They're really important to get pupils to engage with code and get them to sort of behave like the computer, behave like the compiler. And when I do this, I don't use the formal GCSE way of doing it at all. I will have the program or an algorithm written on the board, and I will just draw a couple of boxes on the board and go, right, here are my variables, here is the output. And I will step through my program and go, right, okay, let's say they're going to enter 8. So, okay, this line has happened, I'll write 8 here. And then we start out with binaries and empty strings, so I'll write binary equals and leave that blank, and then whole equals this, and I will literally write it on the board, and you'll see I'll cross things out. I don't erase them, I cross them out as I'm going to encourage them to hand trace. And the more practice you can do with this, the better. It's really important that they don't like doing this, they like the computer to do it for them, but it's really important they have this ability. And testing is a challenge. Pupils don't like testing their programs. I find that, you know, obviously some generalizing, some really want to make sure they're perfectly correct. Others, even if they don't run, just want to move on. They don't really want to do it. Others will go, hey, it ran, but they won't even check the output. Others will go, well, 7 gave me 12, which is what I expected, but I'm not going to test it with anything else. So I think I build in strategies to sort of enforce testing, but it is important. And debugging is another way of getting pupils to engage with code. And you need to give them ways of doing this, approaches and lots of exercises just to try to get them to practice reading code and trying to work out what's going on. On paper, I think take them away from computers very often and get them to look at things on paper so that they're not sort of relying on the compiler to tell them the answer. They need to be able to figure it themselves. It's important to scaffold. Pupils will learn at different paces. You can do this in lots of different ways. You can give them code and ask them to modify it. You can give them partially completed code, so they've got a sort of starting point and then they add on to it. Things like puzzles are quite good. If you haven't heard of those, I'd definitely look those up. It's a good way of sort of pulling out the common misconceptions and fixing broken code, but you need to keep those examples quite simple. If you make them too clever, they're going to really struggle. So lots of those things I think you can use as strategies for building up their sort of toolbox of programming techniques and computational thinking techniques. So I think that teaching programming is really, really challenging, but my experience, the thing that I found that has really helped is taking really small steps, and guiding them through those steps, taking a spiral approach. So taking a concept in a small way, introducing it, practicing, coming back and increasing the depth each time, making sure there are lots of success points. Pupils need to know they are succeeding, particularly when we are asking them to accept failure so much. I often say to my pupils, if you could write every programming exercise I gave you with no struggle, I would be concerned. Because when it came to something that you found hard, when you hit your ceiling, you wouldn't have the tools, either mentally or in terms of the practice of programming, to actually solve those. And so it's really, really important that they fail and they puzzle something out. And so the flip side of that is they have to have success points. So if you do things in small steps, they've achieved this, they've achieved this, they've achieved this. Maybe the final goal they won't get to, but they've had lots of success points along the way. And reinforcement of all the tools that you've introduced and all the concepts you've introduced, and lots of practice. And I found that these things have made a really significant difference to how the pupils are learning. Well, that's me. I hope that has been useful. I'm sorry I've talked for 36 minutes almost non-stop. That's what happens. But I'm very happy to take any questions.
Yeah, we have got a few questions, so
Excellent.
we'll see how many we can get through. Okay, the first one is from Sabia, and it says, please, could you say the name of the block-based programming that you referred to? She missed the name of it.
I'm not sure which one you mean, Sabia. I talked about Scratch and I talked about Rapid Router, but actually, here's one I prepared earlier. This is in the PDF in the handout. All the links are there. So I'm not sure which one you meant, but the links are all there, Sabia. So hopefully that answers your question.
Yeah, I think it was the Rapid Router one, because that was the slide we were on when she put that up.
Okay.
We have a question from Carl, which is there any evidence that games-based approaches like Rapid Router actually result in conceptual understanding that can be transferred into other programming activities?
Oh, I'd like to unpick that, because actually, although Rapid Router looks like a game, I would argue it isn't, because you're not writing a game, you're not playing a game, you're actually following exercises. So if you have a look in Rapid Router, you will see that you're trying to achieve a certain task. It feels like a game to the pupils, which is fabulous, but actually I wouldn't really classify it as gamified. And I think I have an issue with gamification generally. And so I would kind of agree and disagree with both parts of that question. And yes, absolutely. When you take a really structured approach, and even if you are gamifying, I think the really important thing is that you structure it. You don't just go, right, here's Scratch, let's make something. And I don't want to do that Scratch, because I think Scratch is a wonderful tool, but I think it's essential that you structure it. If you're going to use Scratch, you need to structure it. And then yes, absolutely, they can learn from that. And there's lots of research evidence.
Just to remind people watching the webinar that the slides are available as a download in the handout section under the orange arrow at the top. So please take the opportunity to download those. So you will have a list then of all the software that was referred to. Gobinda asks, which Python IDE would you recommend to use?
Well, I just use idle. I don't use any of the fully featured IDEs, and I do that intentionally because I don't want them to be distracted. I use a fully featured IDE at A level, but before that I don't, because actually I think the very plain text here and there is important for them to not be distracted by windows and buttons. So if I was you, I would just use idle.
Brilliant, thank you. Dominic asks, which mimics do you like in Flowwool?
Gosh, I use a fair number of them. I start with the zebra crossing, which is just really, really simple, flashing a light. I use the traffic lights initially without the pedestrian button, trying to get them to do the sequence of lights on a traffic light, which is quite hard. And later I add in the pedestrian button. I use the bridge lights, so you've got traffic lights at either end of a narrow bridge, because that's great for coordination. I use the greenhouse, I use the lighthouse, I use quite a lot of them. And I use the train set at the end as kind of an extension. But I generally like, the robot I use when I do subroutines. Quite a lot of them, basically.
Sabia's confirmed it was Rapid Router, so she says
right.
Thank you.
Brilliant.
Where are we up to? So many questions. It's really good.
Excellent.
Just a nice comment here. Vic says, it was very useful today, thank you. We only used Scratch for block-based programming before, so thank you for sharing your experience.
Brilliant, thank you, Vic.
We've got 2 more questions. Chris says, why do you use Java for A-level after Python?
Okay, I have taught Python 00. The syntax is quite clumsy. I really like Python for an introductory programming language, but I find myself apologizing for it quite a lot. So you can't have true constants, for example. If you look at the syntax for writing classes in Python, it's awkward, and you can't have true privacy, for example. So I just felt that, for me, and I am quite an experienced Java programmer, wasn't having to learn it. It felt to me, because Java is an object-oriented language and you can't get away from that, that they were ready for that switch. So my first unit at A-level is teaching them Java, and I do it in the kind of classical way of every program is a class, just get used to it. And then later I introduce the object-oriented concept. So the first unit is very much conversion. You know how to create variables in Python, this is how you do it in Java. You know how to create selection in Python, this is how you do it in Java. So it allows you to take that, and they don't take too long actually, but I just much prefer the syntax.
Thank you. Steph asks, do you use physical computing to teach programming?
Only in a pretend kind of way. I'm afraid I don't. I avoid batteries. So I do things like Flowwool. I use the microbits, to be fair. It's about as physical computing as I get, but I don't, in full classes, I don't use things like Raspberry Pis and LEDs. I do those in clubs. I just feel that too much physical computing in a class full of pupils can just end up with far too much distraction. So although I think they're wonderful, I try to sort of simulate physical computing in a bit more of a manageable way.
And Dominic's pressing you for some more information on the Flowwool unit. He said, similar question about the length of the units for that and also Rapid Router. He's curious, as you mentioned, the whole term on Python.
Yeah, I use about half a term on each. So I don't tend to do anything that's less than half a term. I would spend half a term on Rapid Router. Sometimes I come back to it later, and I would spend half a term on Flowwool as well. But I see my pupils once a week in year 7 and 8, and twice a week in year 9.
And that just answers Chris's question, which was how much teaching time do you have for Key Stage 3 computing?
Yeah. So, I think you've got a challenge if you don't see them once a week. I think that must be quite tough going.
And one that I've just missed from earlier, because there's quite a few this afternoon. Where can I learn more about hand tracing, please?
Okay, I think there might be something on my website. If not, I will put it there. But I mean, it's basically, you need to try to sort of be the computer. You need to be very slavish about it and going, right, line 1 tells me to do this, so I write it here. Line 2 tells me to do that, so I write it here. And just having those separate sections, one for the variables and one for the output, to demonstrate that sort of stepping through the code as though you're the computer.
I think that's all of them.
Look at the timing, Wendy.
Dominic's just squeezed one in because we've still got 2 minutes. He writes, last question, I promise.
That's fine.
How do you... Hang on, it's jumped now. Where's it gone? Come back. There we go. How do you like to assess these units at the end? So a question about assessment.
It varies. So in terms, apart from Python, I do a combination, because we know even with programming things, you can do a written test quite easily. So I will sometimes get them to do a thing. So, go and create a flow or flowchart to do so and so, and paste it in this document and, submit it in the school. So I will sometimes do that. In written exams or written tests, I might, even with Python, go, here is a snippet of Python code, what does it output? Or here is a flowchart, what does it output if I enter 7? So you can do it in a combination of different ways, to be honest. I also use some automatic marking. So in year 9, when I'm doing the Python unit, and it feeds back into that issue with testing and how pupils don't. I've used something called HackerRank for Work, and if it's not on my list of links, it should be. HackerRank for Work is free for education. It's not on there. I'll find it. And it allows you to write programming questions, but to create test cases. So you will create a test case that says, and if we enter 7, the output should be 12 or whatever. And the thing that's rather nice about it is you can hide the test cases from the pupils. So I will show them 1 or 2 that are the obvious ways of testing their program, and then I will hide the rest. So it'll just tell them if their program is right or not, and they have to go back and try to figure out how to do it. So lots and lots of different assessment strategies depending on what you want to do.
Thank you. Rebecca, is your website address on the PowerPoint anywhere?
It is.
Oh, perfect. So
yeah,
that answers the really last question from Adam.
Fine. I'm just going to put it there. Perfect. There we go.
You can send it out to all if you put it in there. Perfect.
Yeah, go on, keep talking. I'm zooming.
I'm going to echo the words of lots of the attendees just to put their comments in at the end of your session, saying excellent, thank you for sharing your thinking strategies, a great session, really informative.
Oh, that's nice.
Brilliant, amazing, and they just go on and on. So,
wow, that's lovely. How nice.
So can I say thank you so much, Rebecca, for presenting this session, and thank you so much everyone who's joined us this afternoon for it. Please share your highlights from today's session via social media and our CAS website. And at the end of this webinar, a short survey will appear on your screen, and we'd be really grateful if you could take a minute to complete it. Additionally, in about a week's time, you'll receive an email with your CPD certificate confirming your attendance at this session. A recording of the webinar will be available on the CAS website in the near future. And coming up next, I'm pleased to let you know that we have sessions on computing role models, Cyber First Update, and starting your own code club. We hope to see you at other sessions, and please do continue to spread the word about the first ever CAS Virtual Showcase. Thank you so much for joining, and I hope to see you next time.
Brilliant. Thank you. Goodbye all.